And welcome back, students. As we dive into our next lesson, today we are going to explore the concept known as hash tables. Now, hash table is another data structure that we can look at. We've already talked obviously about linked lists pretty extensively, and we're still going to need linked lists in order to use the structure. But remember, we talked about hash tables in some way that's a little bit more efficient than how we have the linked lists by themselves. So, with that being said, with the hash table, this is also known as a hash map, but it's a data structure that efficiently will store and retrieve data from memory. Now, there are many ways to construct a hash table. There's not necessarily one bridge way, but in this section that we're going to look at, we're going to ultimately use an array in combination with single linked lists. So those two things in conjunction will form our hash table. Now, in the previous lesson, we saw that a linked list generally requires linear, or big O of n, steps to determine if a target is in the list. In contrast, a hash table has the potential to execute a fixed number of steps to look up a target regardless of size n. We saw that a constant lookup time is written as big O of 1. However, the hash table we may present here today may still require n steps, but ultimately such a case is pretty unlikely. All right, with the hash function, this is an object that is stored in a hash table by associating it with some kind of key. Then, once we have that key, we can retrieve the object. Ideally, that key is therefore unique to each object that you've created. Now, if the object has no intrinsically unique key, well, then we can just use a hash function in order to compute one. In most cases, the hash function computes a number. For example, let's use a hash table to store dictionary words. Such a table might be useful to make a spell checker, for example. Words that are missing from that hash table might be words that are considered to be spelled incorrectly. All right, there's this concept known as collision and chaining with hash tables. So we're going to ultimately construct a hash table with a fixed array in which each array element references a linked list. The key computed by the hash function will therefore map to the index of the array, and the actual data will be stored in a linked list at the hash values index. So, how does this actually look? Well, the display array illustrates the idea with a fixed array of 10 entries. Right? You can see we have our hash array equals new linked list 3, size. This is, of course, a size 10. Initially, each entry of the array hash array contains a reference to an empty singly linked list. Now, first, we're going to add in the word cat, which has been assigned the key or hash value of 2. Next, we're going to add dog and bird, which are assigned hash values of 4 and 7. Now, each of these strings are inserted as the head of the linked list using the hash values index of the array. Finally, we'll add turtle, which you notice also has a hash of 2. Of course, we did have a value there, so what happens? Well, because cat's already stored at 2, we now have what's known as a collision. Both turtle and cat map ultimately to the same index within the array. When this occurs in a hash table with something known as chaining, we simply insert the new node onto the existing linked list. So it's an array of linked lists. So that node is now part of that list. In our example, you can see there are 2 nodes at index 2, which was turtle and cat. The other ones were linked lists of size 1. Well, this one's now linked list of size 2. So if we want to therefore retrieve a value from the hash table, we first compute the hash value of the target. Then we search the linked list that is stored at the hash value or hash array hash value for the target using an iterator to sequentially search the linked list. If the target is not found within that linked list, then the target is not stored in the hash table. If the size of the linked list is small, obviously, the retrieval process will be pretty quick. So a simple way to compute, therefore, a numeric hash value for a string is to sum the ASCII value of every character in the string, and then compute the modulus of the sum using the size of the fixed array. So, for example, we can say private int compute hash string s equal, we have int hash equals 0, for I equals 0, I is less than s dot length, I plus plus, hash plus equals s dot char at I, so we're adding the character, and then return hash mod size, or in our example, remember size was 10. So, If we kind of look at an example here, the ASCII codes for the string dog are as follows. All right, D to 100, O is 111, and G is 103. The hash function, therefore, is computed as follows. Sum, I'm going to add 100, 111, and 103, get 314. And then the hash is equal to that sum mod 10, because remember, we have an array of size 10. So we get 314 mod 10, which of course equals 4. In this example, we first compute an unbounded value, which was the sum of the ASCII values in the string. However, the array was defined to only hold a finite number of elements. Remember, it was 10 elements. So if I wanted to scale the sum to the size of the array, we compute the modulus of the sum with respect to the size of the array, which of course was 10. In practice, the size of the array is generally a prime number larger than the number of items that would be put into the hash table. So it's going to be a pretty large number if you have a big data set. Now the computed hash value of 4 will ultimately serve like a fingerprint for the string dog. However, different strings may ultimately map to that same value. Now we can verify another one, for example. Let's look at cat. Well, we can verify that it maps to, you can see we got 99 plus 97 plus 116, mod 2 equals 2. All right, in turtle, there was another one. We did 116 plus 117 plus 114 plus 116 plus 108 plus 101. Take that sum, mod 10 again, and we get 2. Now, if we want to look at this from a coding perspective, because obviously this is really good for all theory stuff, we actually have some code that we can look at here. But before we get to the code, and I'll show you that in just a minute, I want to talk about the efficiency of hash tables. Remember, we said that they can be a lot more efficient than just a linked list by itself. Well, the efficiency of the hash table ultimately depends upon several factors. First, let's just look at the extreme cases. Now, the worst case runtime occurs if every item inserted in the table has the same hash key. So pretty much, if like everything was stacked up at linked 2, where it was like everything came back as 2, well, everything's going to be stored then in a single linked list, which of course, now it's got to go through that whole list. And with n items, well, the operation is going to require big O of n steps. Fortunately, if the items we insert are somewhat random, then the probability that all of them will hash to the same key is pretty unlikely. All right, you're ultimately going to try to end up with something that's all scattered out through and have linked lists of different sizes and stuff like that. In contrast, the best runtime performance occurs if every item inserted in the table has a different hash key. This means there's no collisions, so the operation will require a constant or big O of 1 steps because the target will always be the first node in the linked list. So literally, let's say you have an array, because we're using arrays and linked lists again, let's say an array of size 50. And that simply says, let's say we put 50 elements in that array. Well, each element that we put in there ended up with its own value. So it's at its own spot within the array. So you have 50 linked lists, all size 1. Now, we can decrease the chance of collisions occurring, ultimately, by using a better hash function. So, for example, the simple hash function that sums up each letter of a string ignores the ordering of letters. The words rat and tar, for example, would hash to the same value, even though they're different words. A better hash function for a string is to multiply each letter by an increasing weight depending upon the position of the word. So, like you could say if it's at position 1, you're going to multiply by 1. If it's at position 2, multiply by 2, etc. So here's an example. I have int hash equals 0. For I equals 0, I is less than s times length, I plus plus. Hash equals 31 times hash plus s dot char at I. So you can see here, the hash is getting multiplied by value, and then we're adding the char at I. All right. Now this all leads to something known as the time-space trade-off. So another way to really decrease the chance of collisions is by making your hash table bigger. We kind of already said that. Bigger hash table, you have more entries, right? Well, for example, if the hash table array stored 10,000 entries, but then we're only inserting 1,000, well, then the probability of a collision is much smaller than if the hash table array stored only 1,000 entries. Because rather than doing 1,000 to 1,000, I have 1,000 for 10,000. I have a lot more space to stick stuff in there, right? However, there is a slight drawback to creating an extremely large hash table array, and that's wasted memory, because you're allocating, hey, I need all the space for this structure. Great. But now it's just sitting there. It's not being used. Now, if only 1,000 items are inserted into the 10,000 entry hash table, well, then you have 9,000 memory locations being unused. So there's 9,000 things in memory just waiting, but they're not doing anything. All right, this illustrates what's known as the time-space trade-off. Sure, you're increasing your time of your program, but the trade-off is that you're taking up more space, more memory within your program. Now, it's usually possible to increase your runtime performance, so if you want a faster program, at the expense of requiring more memory space, and vice versa. So if you want greater speed, you're going to need more memory. Right? If you don't care about speed, well, you need less memory. So that's kind of the tit for tat with it. They kind of work in tandem with that. All right, and that wraps up the notes section. So let's quickly pop over to Eclipse, take a look at our hash table here. And you can see we have a hash table class. We're using the linked list 2 structure. We're just going to call that hash array. All right, and what this does is it creates a hash table. All right, here, of course, is the array that's being constructed of that. And of course, we have this one hard-coded to a size 10. All right, then we compute the hash itself. This is what actually will put that value in here. And remember, if you wanted to, like when we looked at the ones with summing a string, this is where you would modify this to become like multiplied by a value. So that way it's not just adding in s.char at I. All right, we have a boolean here, which simply looks to see if it contains a string. And we also have a put, which will store or put a string into the hash table. So if we look at our demo code to see how this actually gets implemented, it's actually pretty simple. So we are going to construct our hash table, and we're going to add items to it simply using the .put. So h.put dog, h.put cat, h.put turtle, bird, etc. All right. Once I've done that, this is simply just looking to see if it contains those items. All right, because this puts it on there. So remember, this is using the method we just discussed in the notes, which is looking at the ASCII value characters of the string. So if we run this, we can see it's adding dog, cat, and turtle. It contains dog, yes. Cat, yes. Turtle, yes. Bird, yes. Fish, no. Cow, no. All right, so a very simple program to kind of help you see how a hash table can work. All right, so the linked list, of course, you still need linked list structure, which I gave to you again in the notes materials for this lesson, so you have it again. And of course, here's our hash table, which actually constructs that, and then here's a simple code to run it. All right, with that being said, folks, hopefully that gives you a little bit of experience. I might leave you some resources to other things on hash tables within the materials as well. But I will see you next time.